Welcoming our first speaker, Professor Dishant Pancholi. Dishant is a mathematician at the Institute of Mathematical Sciences in Chennai. He has been recognized for his work by the Birla Science Prize 2018 and the Shanti Swarup Bhatnagar Award 2019. But more importantly, and pay attention to this, his contributions have advanced our understanding of symplectic and contact topology. So he's going to speak to us today about embeddings of four manifolds in triple product of the sphere. Dishant.
So I'm going to talk about embeddings of four manifold. Well, embeddings means you are going to realize a particular space which I call manifold, which is like a surface, which is some nice smooth structure on it, inside some ambient space, so that you can, this kind of things helps you in constructing invariants of spaces, geometric spaces. So the question I'm going to discuss is that now if you are, this manifold has different dimensions, like for example one dimensional manifold is circle, two dimensional manifold is a two dimensional sphere like a surface of a tennis ball or a surface of a donut. So these are example of two dimensional manifold. So one given any n dimensional manifold, one can ask how can I view this n dimensional manifold in some bigger space, which is called, it's embedding in a bigger manifold. So, and ideally one would like to understand the smallest dimensional space in which we can see this, so that so the question is that given n, what is the smallest k such that every n dimensional manifold embeds, you can ignore terms like smoothly and so on, embeds in a fixed manifold of dimension k. So this is the technical thing that I am going to assume manifolds are connected orientable, but for most purpose we can right now ignore that. So what we know is that when n is odd number, then if n dimensional manifold always goes into sphere of dimension 2n minus 1, and this means that every three dimensional manifold, which are of real interest because of its dimension, we are living in three dimensional world, they would go inside a five dimensional sphere. And so the natural question is that well, it is the best thing you can expect for three dimensional case, because it is known that there is no four dimensional space in which all the three dimensional space embed. So natural question is, what about four manifold? Because of course if you include time, then even four dimensions are important. So in which dimensional space or manifold all four dimensional manifolds embed? And so what I want to discuss is this result that this every four manifold embed inside CP1 cross CP1 cross CP1, which is nothing but product of CP1 is nothing but just two dimensional sphere. It is just a fancy way I have written, but it's just usual two dimensional sphere. And if I take Cartesian product of this sphere with its three times, then that's the space I am considering. And the statement is that every four dimensional manifold or every four dimensional geometric space embeds inside product of three of these round spheres. And it is known that all four dimensional manifold cannot embed inside six dimensional sphere. They embed only if these manifolds are spin, which many people may be familiar with this terminology. So if this four manifold admits spin structure, then it is possible to put them inside six dimensional sphere. Otherwise you have to work with spaces which are slightly more complicated geometrically than just a nice sphere, and one such space is product of three two-dimensional spheres. So what I need to explain to you roughly the proof is a decomposition of 4-dimensional manifold. So any such object, 4-dimensional manifold, is actually union of 3 subsets, or you can say 3 parts. So you can decompose your 4 manifold into 3 parts, and these 3 parts comes together with a function to the 2-dimensional sphere, which satisfies these 3 property, that part A, meaning A is under this pi, is sent to the upper hemisphere of the 2 sphere, part B is sent to the equator, and part C is sent to the lower hemisphere. So you have kind of decomposition of your manifold into 3 parts. The first part is sent completely to the upper hemisphere, the middle part is sent to the equator, and the lowest part is sent to the lower hemisphere. And we are going to use these 3 pieces and embed each piece separately, and then in a way that we can patch those embeddings together. So let me describe the first part. The first part looks like, so what I have drawn below is a upper hemisphere but kind of flattened out. So upper hemisphere looks like a disc, but which is kind of curved like this. I have just flattened out by heating on the top. And then if I look at this, what it looks at every point of this upper hemisphere, if I look at the inverse image, the thing that is mapped under pi to this point is either a surface, which is like a surface of, as I told you, a surface of a donut which I have drawn, or maybe slightly more complicated, many donuts, just like a donut with many more holes than just one hole. So, but there are some points which I have denoted by X, where this nice donut picture sort of disappears, and you actually get some kind of singularity where a curve on this donut is pinched to a point. Okay, so that is the part A. So part A looks like this. Part A just looks like this pinch donut times a circle, which is the equator. So what I was explaining is that the part B looks like this singular donut with a circle pinched, surface of a donut with a circle pinched times equator, and the third part looks like this circle which was pinched is chopped off, and a 2 nice disc is attached to it times a disc. So it will be what is known as genus G-1 surface. If the original donut had K punctures, then this will have K-1 punctures. So what we'll do is we'll embed each part separately. So let's recall that X is A union B union C, and part C, what we know about part C is that part C is just this a smaller number of punctures donut times the lower hemisphere, where L is the lower hemisphere. And so if you find an embedding of surface inside CP1 cross CP1, which is very easy to find because every surface that you can think of actually sits inside 3-dimensional space, so it trivially sits inside 4-dimensional space. And so this guarantees that there is an embedding of part C into the product of 2 spheres times the lower hemisphere. Now a little bit of trick allows us to, which is called local model of singularity, allows us to extend this embedding also along the equator, because on the equator there is some singularity which I have written in explicit coordinate. It looks like x square plus y square minus z square, the singularity at 0 of this polynomial. And so whatever we have extended can be extended to the lower hemisphere union equator. So what remains is to extend this embedding which is given on the lower hemisphere including equator to the upper hemisphere, and the part that we need to extend is the part A. And let me recall that previous picture, that part A was something like this. There was upper hemisphere, and inverse image of every point was either a nice k-hole donut or a k-hole donut on which a particular curve is pinched. So to extend this, we need the notion of flexible embedding, and I would like to give a sort of a baby model of what this flexible embedding consists of. So here is a model. You take pair of point P comma Q, then the two obvious transformation that you can think about this two point is that P going to P and Q going to Q, or P going to Q and Q going to P. So these are the two transformation, or we will call in topology system these are two homeomorphisms. So now, but there is no, if you just look at this set of points P comma Q, then there is no way you can make these two transformation transform from one to another continuously by one parameter family, because they are like a just discrete set. But if I think of these two points P comma Q as a point of a unit disk which I have drawn here, and if I rotate this unit disk by 180 degree, then, and I can do this rotation continuously starting from 0 to 180, then I can kind of move Q to P and P to Q. A two-dimensional generalization of this notion is what I have drawn in that picture, which just says that I have a transformation from sigma to sigma, where sigma is the surface of k-hole donut, and I want to put this sigma inside product of two sphere in such a way that inside the product of these two sphere this sigma moves around, and when it comes back to itself, it does not come back to itself as identity, but it comes back to itself as a transformation phi. And a theorem of Hirose says that such kind of embeddings of surfaces are indeed possible inside product of two sphere or product of CP1 cross CP1. And so we use this to, this is the key ingredient we use to, originally we had defined an embedding, for any embedding we could produce an embedding that extends to equator, and now we have to restrict to this particular embedding which has this property that the transformations, any transformation of a sigma, which I will call it diffeomorphism, any diffeomorphism sigma actually comes from a continuous transformation of CP1 cross CP1. And so you use this fact and the fact that such an embedding is possible to glue, to extend the embedding that was already there on the lower hemisphere union equator to the upper hemisphere, and that's the basic idea of proof of this result. So thanks.
Well, we have, thanks Dishant for finishing well in time.
Thanks to you.
We have time for questions, so.
We talk about 2-qubit Hilbert space. In quantum physics, we talk about 2-qubit Hilbert space.
Yeah.
A single qubit Hilbert space is CP1. 2-qubit is supposed to be CP3. Complex project, 2n plus 1.
But it is
CP3. So I wonder what is the connection between CP1 cross CP1?
Yeah, because it is 4-dimensional complex space and you are identifying the lines to.
Yeah, exactly.
Yeah, sure.
So I'm wondering whether there is any connection between that and your CP1 cross CP1.
No, there is no. For this particular existence of CP1 cross CP1 has no connection with that fact.
That's CP3, I see.
But what is true is that every 4-dimensional space indeed can be seen inside CP3, which is the Hilbert, which is the thing you are talking about. Yeah.
Thank Dishant for a very nice talk.